Technical University of Munich, and Institute of Nanotechnology, Germany. He has a wide variety of interests. Some of his interests are in ultra-cold atoms, light matter interactions, the atomic clock, and of course, quantum information theory. Today, he will talk to us on formation and dynamics of supersolid and quantum droplets in dipolar dBEC. So he will be emphasizing the role of quantum fluctuations, crossover from superfluid to supersolid phase, and exotic quantum droplets. This is going to be a very interesting talk in condensed matter physics, but with direct relevance to quantum information. I invite Dr. Sonjoy Majumder to commence. Perhaps you should just share screen.
Thank you, ma'am. Can you hear me now?
Yes, we can.
Yeah. Let me try to first share the screen.
Yeah.
Is my
yes,
screen
yes,
visible?
Yes, it's visible.
Let me put it in full screen mode.
Okay. Yes, it is visible.
So, good morning, everyone. So it's a quite pleasure to speak in front of you, especially I know ma'am for a long time. Today's presentation, I thought I'll talk about some of the recent work which we have been doing. Okay. And it's about the quantum droplet and quantum supersolid, which are the distinct phenomena of the Bose-Einstein condensate, which will be very, very interesting in coming days of physics, okay, and technologies. So before going through that, getting in the topic, let me introduce the kind of work we are doing in the IIT Kharagpur. So basically our interest in the ultra-cold atoms, and recently we are getting into supersolid droplets, okay, also in spin systems. Then we work a little bit of astrophysics, neutron observations, then on the some things on the topological matters, okay, and it's quantum computing, quantum machine learning, like that. Okay, so this is the present undergraduate students working with me. Okay, so today's for today's presentation, I would like to discuss these two papers, recent papers. One was published in Physical Research and last year, and one just accepted. Okay, so we'll discuss about these two papers. Since this presentation is for mostly aiming to the undergraduate students, I thought there'll be some introductions required for BEC, because this may be the first talk in the BEC or Bose-Einstein condensate. So let me just briefly talk about the introductions part. Please, the experts, please bear with me. So as you see the cartoons, okay, these are the laser cooling technology which is used to condensate a enormous number of atoms, okay, which are in the gas form, okay, and these are known as laser cooling technologies, okay, and subsequently there will be something which is called evaporative cooling. Those who are not aware, please maybe look at the different references, which will tell that how these cooling technologies actually can make the gas of atoms, okay, condensate. And these So experimental scenario, which we can theoretically depict using a harmonic trap, where actually you can think about that the atoms are cooling down or losing the energy and trying to occupy the ground states. Okay, so this will be the picture where you can have that all the atoms coming to the, almost all of the atom coming to the ground state and making a coherent state, which will be appear to be like a laser light, what we know that. Okay, so it also known as the atom lasers. These techniques of laser cooling, as it is very well known, and there's a well-known application in atomic clock, as you know, where actually we can nowadays getting the very good uncertainties of this amount, 2 into 10 to the power minus 18. Okay, so these may be the one of the motivations to look for the ultra-cold atom for the Bose-Einstein condensate. So let's get in that what actually the Bose-Einstein condensate. Okay, when we talk about that, it is a different state of matter. Some people say it is the fifth state of matter because its gaseous forms still in a very cold temperature. Okay, so if you see that, if you pull down the systems from 300 nanokelvin to the slowly going down, and if you look at that 2D velocity distributions, okay, so this may be a different direction or x and y direction, the velocity distributions, you see that you are getting cold to the ultra, this is the ultra cold, but not at condensate, but there is a certain junction where you see that the atom, most of the atoms comes to a ground state and you will get a peak. Okay, that may be at 100 nanokelvin or of the order. Okay, so what would happen that these at this temperature, okay, all the atoms, okay, come down to the ground state. Let's say almost all of the atoms. Okay, so there'll be some stray atoms which will be in excited states. Okay, so if you see that characteristic of this state of matter, so if you talk about a density, that this will be density wise 10 to the 5 times less dense than the normal air. And for this ultra cold experiment, this is the workhorse. Okay, so the different experiments, okay, can lead to the new technology in modern era. If you look at that de Broglie wavelength, okay, so this goes by square root of 1 upper square root of the MT. So that for given a mass that of the atom, if you see that if you go to the lower and lower temperature, de Broglie wavelength becomes larger and larger, so that you can get a large wavelength, okay, of the for the condensate. And these will be appearing like a giant atom, or people say that, as I said, it's a kind of a coherent states of the matter. So it will be like a atom lasers. Okay, so these kind of atoms, okay, is very useful not only for the technology, it is also useful for the theoretical purpose. Also, people can look at different many body phenomena, okay, and study them using the quantum simulations. Okay. So presently, if you look at that periodic table, the atoms which are being used for this Bose-Einstein condensate are mostly by the alkali-like atoms, okay, in the first column of the periodic table. But there are other atoms which also be very useful, okay, and they have been demonstrated as a candidate for the Bose-Einstein condensate. The interesting phenomena is that those who are actually not alkali-like, okay, like this kind of that cadmium, chromium, or terbiums, okay, DY, ER, erbium. So there are many of them. Okay. And few of them, as you see that they are in the series of the lanthanide. Okay. And we are actually interested here, few of them which has the strong dipole moment. Okay, and we'll look at it. Okay, so when we talk, so we are not talking about the experimental part, we are talking about the theoretically how to understand this. So first of all that, okay, we have that trapping potential, which actually trap all the atoms, okay, and you can mimic that trapping potential is the harmonic potential like this one. In 3 dimension, you have the different frequency of the oscillations of the harmonic oscillation, omega x, omega, omega z. You can play with the different values of omega x, omega y, and omega z, and making it a quasi 2D or quasi 1D. Okay, like you can have that quasi 2D trap, making that omega x equal to omega equal to omega, and whereas you can have omega z, which is in the z direction, the oscillation is very large. Okay, so that you're confining in the z directions, the distribution in the z direction, and it will be distributed in the xy direction. So this is one of the examples of a 2-dimensional condensate in the trap. Okay, so you have all the atoms, maybe they are actually coming down. And then apart from that, so you will have the Hamiltonian for the systems where you have the kinetic energy part and the trap potential. Apart from that, you also have that atom-atom interactions, which plays a very interesting role, especially when you are talking about the many body physics part. It plays a very interesting role and giving the new phenomena in the condensate. Okay, and these can be studied experimentally and easily. Okay, so here, being that dilute systems, we can consider that this is the condition that atom-atom interaction can be a kind of contact potential, which we can approximate using the S wave, and that means that when the one atom will be in touch of the other atom, then only we will have a non-zero value of the potential. And this can be actually amplitude-wise can be accounted using the scattering length, which is A scattering. Okay, and it also depends on the mass. Now, once you have understood that Hamiltonian for the normal Bose-Einstein condensate, okay, where we have these few terms, okay, that kinetic energy, trap potentials, and atomic interactions, you can see that these condensate can also be tuned, okay, using some kind of a technology which is known as phase-back resonance. It's like that when you have the atoms are coming close, okay, in a suppose in a container, okay, and they are actually, you can think about far away from each other, but they have a possibility to form a molecule. So if you see that dissociation energy diagrams, if you see my cursor, okay, so these will be that closed form and closed channel, some people say, and there will be open channel when they are not actually forming a molecule far away from each other. But by tuning the laser light, you can have the transition between these two, okay, which is actually known as phase-back resonance. And by tuning that frequency and magnitude of the or intensity of the light, okay, what you can have that you can control the atom-atom interactions. Okay, so that's actually a novel technique, okay, to tuning these atom-atom interactions, which we are talking about the last part of the Hamiltonian. Okay, so if you can tune this, okay, you can have a new technology or new kind of a demonstration of the experiment can be obtained using this technology. And recently in our PRL paper, we have shown that using the magnetic field also, you can tune this kind of interactions, which is using the magnetic, that phase-back coil or magnetic coil, okay. So what we actually want to say that in this Hamiltonian, okay, Apart from that, tuning that trap potential, which actually done by tuning the frequency of the harmonic potential, okay, there is another part which is atom-atom interaction, which also can be tuned or modulated. Okay, so these two actually can be done from the external field. Okay. So using this, if you understood this one, okay, you can see that you can achieve the condensate. Okay, this is the typical single shot image, okay, of the density profile of one of the important candidate of atoms, that is DOI 162. It is this is that. So you can have the different variant of the DOI, which can be also condensate. Okay, and if you see that at different temperature, okay, there's 179 nanokelvin, and if you go down to 94 and 47, what you can see that you can get that the condensate forming at this temperature, and you can see that the thermal profile, okay, which will show that is really, okay, the condensate forms. Now, having that understanding or visualization that there is a possibility to form the condensate at that ultra cold temperature, okay, for these atoms, okay, there are different possibilities of applying this condensate in the technology, which are known as quantum technology. Nowadays, these actually are proposals, okay, mostly these are in proposal form, okay, that using this condensate, you can have the different quantum computations, you can have the quantum network, you can have different quantum information processings, okay. So different examples actually are discussed in these papers. If you are interested, you can look at them, okay. So the directions motivated from this paper are actually, you can see that quantum algorithm mapping between QIQT and dBEC qubits, okay. Decoherence minimization schemes of which can be obtained from the creating entanglement using the different components of the dBECs, okay. Even there are one variant of the dBEC which has a spinor signature, which are very useful for this entanglement. Okay. So all these experiments or these protocols, okay, which have been proposed, there are some experiments are also there here. They manifest that in these cases that quantum control is the main driving force, okay, to do this kind of experiments, okay, or to achieve this kind of technologies, okay. So unless this quantum control, you can't have actually different protocols to be formulated, okay. So what people mostly use in these cases, they uses that different components, multiple components, BECs for this kind of technologies, okay, since it is a conference or symposium for this quantum information and quantum computing. Okay, so what I would like to address that these kind of technologies, okay, also is possible using Bose-Einstein condensate. And here, mostly people uses that multiple component BEC using that different hyperfine state. Okay, these are actually if you don't know, these are the states actually coming due to the spin component of the nucleus of the atoms. Okay, so that's actually can give that different components of the BECs. Okay, and finally, what the control mechanisms is that among these components, okay, the interaction can be controlled, okay, using phase back resonance, either using external magnetic field or electric field. Okay. So there are different areas are popping up nowadays in modern physics or modern research in science and technologies. Okay, The few of them are enlisted here. The thing is that these atom-atom interactions manifest the excitation spectrum of the BECs. They are having that different signature, okay, of the collective excitations. Like that, you can see that vortices generated, the quantized vortices generated, okay, inside the condensate. You can have the point vortices, you can have the center of mass vortices, okay. You can have that this point vortices can generate the vortice lattices, okay. There you can have this collapse and expansion explosions of the BECs, which is well known as Bose-Nova, okay. They can be achieved by suddenly changing that atom-atom interactions, okay, from attractive repulsive or repulsive to attractive. So you can formulate them. Similarly, the other directions, okay, where actually people can look at the quantum phase transitions from the superfluid, which is actually Bose-Einstein condensate. From there too, you can see that Mott insulator phase, okay. So these can be obtained from the sophisticated interplay between the external potentials, quantum statistic, and interparticle interactions. Okay. There are another directions or another features which is very, very important at the present day physics and technologies. Okay, these actually which we'll be discussing here, the first and second order phase transition. Okay, which can be obtained when you see that the superfluid can go to the some kind of a crystalline phase of the condensate, which known as the supersolid. Okay, so they have the crystal structure kind of feature, and what we'll see that they have the periodic modulations of the macroscopic wave functions. Okay, so these actually observed only in the dipolar BECs, where actually atoms which is used for the BEC are having the permanent electric or magnetic dipole moments. Okay, so those Bose-Einstein condensate, okay, can show the feature or show the phenomenon that conversion from the superfluid to the supersolid. Okay, so interesting phenomena here is that you will have a spontaneous breaking of the rotation and the translation symmetries. So what we'll see that this will have a crystalline phase and ordering of the wave matter. So because this actually has atomic structure and a giant wave, some people talks or some of this nomenclature of wave matter is used for these systems. Okay, the Bose-Einstein condensate. So this last one is very interesting and which actually we are going to emphasize in this presentation today. Okay, so these first and second order phase transition also can be depending on the geometry of the trap. Okay, so it is a one dimension or two dimensions, which we'll discuss maybe in the coming slides. Okay, so let's discuss about the dipole moments. So this is again for the undergraduate students. As you know that in atoms, nucleus is sitting at the center of the atoms and electrons are almost isotropically distributed around the nucleus. So initially we don't see any kind of a dipole moment, okay, in the atom. But what would happen using external field or due to the structure of the electrons distribution, okay, there may be that asymmetric of the charge distribution in the atom, which can actually generate the electric dipole moment. This is the intrinsic electric dipole moment if it is due to the internal structure of the electron distribution. If you also can apply external electric field and induce that dipole moment in the atom. So that is induced dipole moment. Similarly, you can have the magnetic dipole moment, which is known as in a short form mu, people uses. due to the asymmetry of the spin distribution of the electron and protons. Okay, so in cases, in some of the atoms, okay, they show that non-zero value of the mu, that magnetic dipole moment. And at present, we are interested about those atoms, okay, forming the Bose-Einstein condensate, okay, having the each of the atoms having the permanent dipole moment, okay, the magnetic dipole moment. And once they form the condensate, we call them the dipolar BEC. Okay, so this is the nomenclature which is used when we get that Bose-Einstein condensate using the atoms which has dipole moment, we call dipolar BECs. So there are very famous candidates, okay, like some of them are alkali atoms, some of them are non-alkali atoms. So as you know that lithium, sodium, potassium, these are the very rubidiums, they are actually very well-known candidates for BEC, but many of them have very either negligible or a small value of the dipole moment. Whereas there are systems, okay, like chromium, diazium, and iridium. So they had actually very strong, large dipole moment, magnetic dipole moment. In terms of the Bohr magneton, if you see that chromium has 6 times of the Bohr magneton, dy has 10 times of the Bohr magneton, ER has the 7 times of the Bohr magneton. So they are ideal candidate for the dipolar BECs, okay, because they have a strong magnetic dipole moment. Okay. So we will be interested to explore them. Now, once we have the condensate, so apart from the trap potential, apart from the atom-atom interaction, now because we have the atoms which has dipole moment, these dipole-dipole interaction will pop up. Okay, these are the long-range interaction, as you know. Okay, so now if you just look at that kind of a expression for these dipole-dipole interactions, they will be can be written expresses like this form, okay, which actually one can write it 1/3 of mu naught, okay, times mu a square. So these are the magnetic moment of that atom. Okay, so in terms of the interaction length, one can write it in these forms. Okay. Now, what would happen that since these are the dipoles, they have orientations, and these orientations can be in the XY direction or perpendicular to the XY direction or in some angle to the XY directions. So if XY directions, what I'm saying that means that it is the directions between the two atoms. So this is the R minus R prime, let's say. Okay, so that these are the directions, okay, which actually we are talking about the between the two atoms. And if your dipole moment is oriented by an angle theta or let's say phi, I will be using phi later on. Okay, so that orientation is very important when you talk about this interaction strength, because what we see that interaction strength for these dipole-dipole interactions, okay, not only have the GAA in terms of GAA DD terms, okay, but it will have after the integration over the angle, okay, what we get that 1 minus t cos square phi by this R minus R prime cube. So it also depends upon the phi. So that means if phi equal to 0, this will be normal in the dipole-dipole interactions. But you can tune this, okay, the dipole-dipole interactions, okay, by changing the phi, okay, or here is theta in the picture. And these orientations of the dipoles, as you know that this can be controlled by external magnetic field. So that depending upon the direction of the external magnetic field, you can control these dipole-dipole interactions. Okay, so that this is the example of theta equal to pi by 2. You will get simple form of this dipole-dipole interaction. Similarly, if you can get that theta equal to pi by 2, this cos square terms will be 0. Okay, and similar cos phi equal to 0, it will have this will be maximum, so it will be negative. Okay, so you can see that the variations, okay, of the dipole-dipole interaction you can achieve using by changing the direction of the magnetic field. Okay, so why this dipolar BEC is so interesting? Okay, so that's maybe the first things to understand. So what would happen that people have observed a new phenomena, okay, in the superfluid systems. Okay, once we have this dipolar system, as I have mentioned briefly in the previous slides, what we see that when you play with these dipole-dipole interactions compared to that atom-atom interaction, which I'm just abbreviating with the G, and this ratio, I'm just writing it epsilon dd. And when you modify this epsilon dd from, let's say that 1.42 to 1.45 and 1.40, you see that there's no discontinuity in the density profile. Okay, this is that integrated density profile in y-x state, what we are plotting here. Okay, and when we just see that when it modifies to the epsilon dd equal to 1.45, we see some of the distinct features. Okay, so people who are interested can look at this paper, that we see that the periodic features, okay, the crystalline features which will come. So this clear that anisotropy, okay, of the density profile we can see, and this anisotropy is arising because of the anisotropy in the dipole-dipole interactions. Okay, and these anisotropy in the density can be tuned, okay, or I used to say that epsilon dd, which is actually the candle for the dipole-dipole interactions, can be tuned continuously by changing the phi, as you have seen, and also by changing the atom-atom interaction using the phase back resonance. Okay, so what you see that there is another demonstration of this. Okay, when you change the EDD from 1.31 to the 1.52, we see that periodic features actually propping up. This is rho x versus x. Okay, one dimension the picture, if you see that, they are popping out distinctly. Okay, this was the superfluid. When you have the one epsilon dd is 1.31, when you have epsilon dd 1.42, also the superfluid. Slowly, when you have that epsilon dd 1.45, we have the density profile is this one, and in one dimension you can see that you will get that all the harms are coming of the densities, and that can be enhanced. Okay, when you get the epsilon dd equal to 1.52. So we'll see that clear anisotropy or periodic structure of the density, okay, when we have the epsilon dd equal to 1.45 to 1.52 like that. These are the purely demonstration due to the dipole-dipole interactions playing with the atom-atom interactions. Okay, so what we see that there is a crystalline phase which is popping up in the superplate, which is generally homogeneous kind of in nature. Okay, and these will be very interesting because of their discontinuity in the density profile or anisotropy in the density profiles. So let us talk about that, how we can handle it in the theoretical approach. Initially, in the mean field theory, okay, we considered the Bose-Einstein condensate, which is known as the Gauss-Pitowski equations. Okay, and you can have that is a time-dependent Schrodinger kind of equations, and where the Hamiltonian can be governed by the Hamiltonian which we have discussed, which is due to the kinetic energy, trap potentials, and you have the atom-atom interactions. Now the new addition has come from the dipolar terms, okay, dipole-dipole interactions, which we can write it the last term here. Okay. Question is coming that whether this way of solving this Schrodinger equations at the mean field level is stable or not. How stable? What has been seen that, okay, that the solution of this at the mean field level collapses. Okay. So there is a question of the quantum stabilization of these solutions. And there comes in the rescue comes from the another feature which is very intrinsic to the physics, like that is a quantum fluctuations. Okay. So what would happen that this collapse is happening due to is observed actually when the density increases. That absolute value of the energy also increases. And what would happen that in that cases, energy is not locally conserved. And to make this energy conserved, which otherwise it will be non-Hermitian Hamiltonian. Okay, so we need to add something in the Hamiltonian. Okay, so that these extra terms are coming from the quantum fluctuations. Okay, so these accumulated fluctuations, the vacuum of the excitations. Okay, and these is actually understood from the extra terms, that is quantum fluctuation gamma terms. Okay, and for details one can look at his references. I'm not going to discuss details because of the time constraint. Okay, so this extra term is introduced, which is going by psi cubes here. Now, once we have this extra term, which is also known as the LHY corrections, okay, named about the three famous scientists. Now, the new equations, okay, dynamical equations will be looking like this one. Okay, so we'll have the extended Gauss-Pitowski equations, okay, where we have this distinct four terms, okay, and here actually we can play with the geometry depending upon the choice of the trap potentials, the frequency of the traps. Okay, we can have the quasi 1D using that x directions, maybe that high in terms of the frequency. So, and also in the z direction high in the frequency, whereas the y direction is the very low, comparatively low. So it will be distributed in the y direction. So this is, that's why it is quasi 1D. Similarly, if you can make that frequency high in the z directions, keeping that low value of the frequency in the x and y directions, so you will have a distribution in the xy plane of the density profile. So that will be like quasi 2. So you can have this is kind of a one dimensions, quasi one dimension, this is quasi two dimensions, kind of a dipolar BCs. Okay, and this may be the direction of the magnetic field, okay, which can have that angle phi, which actually giving you the dipole-dipole interactions. Now here, in our case, for these presentations, okay, we'll use dy 164 variant, okay, for the dipolar BCs, whose magnetic moment is 10 times of the Bohr magnetron. Okay, dipolar length is 131 of the Bohr radius. Okay. So here we also consider the S-wave scattering length, and what we will be doing it here, we'll vary the S-wave scattering length, okay, using the phase back resonance, and also consider the different number of atoms in the condensate. Now the results which you see that this is in the physical research paper, okay, So what we see that if you have the magnetic field along the z direction, that means phi equal to 0. Okay, what we'll see that for different values of EDD, which is actually ratio between the dipole-dipole interaction versus that atom-atom interactions, from 1.34 to 1.45 to 1.87. What we see that clear superfluid features, but once we increase the EDD, okay, this is the profile in the XY direction, 2D dimension. What we'll see the some of the nucleation of the density, and around that there will be superfluid. Okay, so this is actually our supersolid phase of the condensate. So which contains that the nucleation of the density, okay, and the different pockets of the XY direction, and there will be superfluid, the uniform distribution of the condensate atom, okay, around this. So this, if you see the structure, this looks like that crystal arrangement. Okay, here as you see that is a hexagon lattice kind of format. Okay, and if you see in the other directions, okay, this from the top view, okay, so this will appear like this. Okay, but once we consider that or once we make that EDD from 1.45 to 1.87, we see a clear distinction of the isolated condensate or isolated condensate forms, okay, which are in the distinct form of the arrangement. Like here, you see that hexagonal structures, but there is no superfluid around this. Okay, so all the concentration of the density has gone inside these points. So these are clear signature of the new phenomenon of the condensate, the Bose-Einstein condensation, that is called the droplet. Okay, so this is the, okay, these are the really distinct phenomena. Okay, and these will be like that crystal, real crystal form of the condensate. And if you view them, okay, from the top, you will see that these are the features, okay, from the top view. So these droplets, okay, are the distinct feature, okay. Superfluid also a distinct feature, but these are also can play important role in the quantum technology. So we have got a new phenomena in the Bose-Einstein condensate, which is called a quantum droplet. Okay, so this dilute liquid-like clusters of the atoms. Okay, they are actually produced, now experimentally shown that in the quantum fluid. So a small cluster of the atom, in cases that self-bound by the balanced attractive and repulsive force, they actually form. So we'll see that anisotropy and long-range character of the dipole-dipole interactions leads to this kind of formations. So these droplets are the filament-like narrow transverse width, and important point, you can orient them along the direction of the external magnetic field. So like here, what you can show that here the magnetic field, as I said, is along the z directions. So the droplets are around the z directions. Okay, so and depending upon the orientation of the magnetic field, you can orient them. So that's the important feature that the quantum contour which I was talking about. This is the real demonstration of the quantum control using the external field. Okay, so this has been experimentally observed for the erbium system, and this is 2018 paper in Nature Physics. They have actually discussed thoroughly of the experimental techniques. Okay. Now, subsequently, okay, quantum droplet have been realized also in the non-dipolar cases, but non-dipolar cases, you need the binary systems, okay? So here one can show that binary homonuclear or heteronuclear cases, okay? Only binary systems, okay, that can form a droplet. These are the different papers which you can just look at. So in these cases, when you have binary system, which we'll discuss at the later part, okay, that there is another feature comes, okay, that whether these two components, okay, of the condensate, they are miscible or immiscible. So that actually plays another role, a very important role to form the droplets, okay. So now coming back to that single component cases, what we have just observed, okay, distinct feature of the phases, okay, depending upon the different orientation of the magnetic field. So the phi is the magnetic field orientations corresponding to z directions, let's say. And what we see that depending upon the EDD value, that is dipole-dipole interactions versus the atom-atom interactions, okay, we can see that the superfluid phenomena can actually be tuned, to the either supersolid, or it can be tuned to the droplet, or multiple droplet, cluster droplet, or it can be single droplet, okay. So what we can show that we can have different phases of the matter, condensate matter, but just by tuning that EDD and the direction of the magnetic field. Okay, so this actually gives a new directions of the control, quantum control, to form the different phase. Okay. Interesting point, if you just look at this four figure, when we change the phi from 0 to 530, 560, 590, the supersolid phase, which is the phase where actually you see that the concentration of the density around the superfluid or inside the superfluid, okay, these actually disappears, okay, as you change the orientations, okay. And also another distinct that cluster form of the droplet, which we saw the hexagonal form in earlier, that also slowly disappearing, and what you will be ultimately going to get that when you have your magnetic field is around 90 degrees along the XY directions, okay. So in that case, you will get the single droplet, okay. So that both the phenomena which you can just observe it, that the disappearing of the supersolid, okay, when you have that the external magnetic field is actually moving away from the z directions, okay, that disappears. Also that disappearing of the cluster of the droplets. These are actually real quantum control here. Here we are plotting that chemical potential, okay, which we can write at dE by dN in terms of, okay. Now, this one, okay, so what we see it here also can be observed, okay, in terms of the scattering length, okay. What we see that there we saw in terms of, here is in some DD, also you can just observe that at particular scattering length, which also they are inside the EDD, they are playing a strong role as you go increasing or decreasing the scattering length, atom-atom interactions using the phase vectors. So what we can say that this phase boundaries, what you see that the demarcation of the different phases, they can be shifted by changing the direction of the field, okay, and it can favor, okay, that superfluid to droplet or supersolid, okay, or vice versa. So supersolid regions is observed at low phi, as you can see that here is, you can see supersolid phases. And also you see the droplet cluster disappears as phi is increasing. And at phi equal to 90 degree, we say that only single droplet is formed, okay, at the surface of the condensate. These also can be understood, okay, if you see the different contributions of the interactions. Okay, this is the contact interaction, atom-atom interaction, the dipole-dipole interaction. This is the quantum fluctuation contributions. If you see, and if you just say that this green curve, okay, which is in the which is becoming positive in this region, okay, from the let's say 22 to let's say 65 around this region, which is actually where your EDD by E contact interactions, okay, so dipole-dipole interaction versus contact interactions, that ratio in this region, okay, for phi equal to in this region, okay, that what we see that droplets are actually formed, okay, and we see that other contributions of the interactions which also play strong role, especially you see the dipole-dipole is increasing, okay, in this region. So we have clearly discussed in this paper. If you are interested, you can just look at it. So just if we concentrate on the single droplet, okay, so we can see that by changing the direction of the magnetic field and changing the EDD, okay, we can make that from a from a disc shape to the elongated shape. Okay, so from XY direction to the so you can change the shape of the droplets. Okay, so that also is a clear demonstration of the quantum technology by external field. Okay. We also see that cluster structure or cluster distributions of the droplets. Okay, so we see that we can change by increasing the phi, which is the direction of the magnetic field with respect to Z. That droplet transforms, okay, from triangular shape to the that triangular shape to the octagon-like and then honeycomb-like shapes in forms. Okay, so this is the integrated profile of the condensate. Another thing is that which we want to highlight here is the number of droplets. Okay, by changing the geometry, the trap geometry, here what we are talking about the scattering length. Okay, in terms of the radius. Okay, from 60 to 75, we see that in quasi 2D cases, if you increase this scattering length, okay, we will be reducing the number. Okay, similarly, it is also same for the 1D cases. So, which says that to get a large number of droplets, you should have the comparatively low scattering length. Okay, or if you want to have a few of them, you just increase the scattering length. Similarly, that in terms of the angle of the magnetic field or direction of the magnetic field, you can see that if you want to have large number of, this is I think clearly understood, large number of droplet, you can have the magnetic field in the direction of the Z directions. Okay. Now, once we understand at least single component dipolar BEC, just briefly talk about that recent publications, okay, which appeared in Physical Review on the binary cases. And we see that really new kind of a phenomena has appeared, that they have appeared in this case of dipolar. As I said that in dipolar cases, apart from that, all the things which you have discussed, there is a new parameters which plays a strong role, that is how these different components are actually overlap with each other. So which characterized by the parameter called miscibility. Okay, how, so if you have that, this is the, if overlap is very good, we'll say that this is miscible, that means that lambda 0 is 1. If overlap is not that, they're immiscible. That is lambda 0 is 0. Okay. So by changing this one, we also can control that the superfluid or that droplet, supersolid and droplets features. Okay. So here is a different cases that in the interesting to see that immiscible cases when there is a overlap 0. Okay, we can see that different features, okay, of the droplets, and as you see that these droplets are alternative components, okay, they are arranged, okay, as such that there's no biasness of that different components. The different colors are actually different components here, okay. So you can have the other combination also, but the center of mass, okay, will be the center of the droplet. Similarly, you can get that multiple droplets, okay. So you can also get super solid phases where you can see the symmetry between the different components and a super fluid. Okay. In the miscible cases, you see that another interesting phenomena is that from these different values, okay, of different values of this one, you can see that supersolid to the single droplet to multiple droplet supersolid and superfluid. Okay, so in the miscible values, okay, from different lambda values, you can just get it. Okay. Another way of controlling, not only using the lambda value, that what you can here do that you can quench the atom-atom interactions and see that different phenomena. So we can continuously change this atom-atom interaction. Here we can have a freedom to have the similar atom, that same component atom-atom interaction, or interatomic. Okay, that means interspecies interactions. Okay, so we can see that since I don't have much time, okay, I just demonstrate and browse it. If there is a question, I can answer later. So we see that the near miscible to immiscible transitions time, what we see that there's abrupt change of that lambda 0 from 0 to 1, and we see that the features, okay, and the droplets becomes from this continuous to that this kind of features. We'll see that due to a sudden change of the lambda 0, we see that this kind of instability has arises in the systems. Okay. So during these times, okay, each components form the multiple periodic segregations, okay, in the domain and the axial direction. So in the axial direction, you see that the segregations. Okay. So this extra domain appears due to the defect. These are the kind of defects, okay, due to the discontinuity of the phase transitions. Okay. The number of periodic domains decreases, okay, with the time, and the final state produces long time evolution. So as you see that in the time domain, okay, so these are the magnetic field and trap was there up to, let's say, 100 millisecond. After that also the droplet sustains, okay, the droplet still exists, okay, after. So there's a long time evolution. We see that, okay, similar to the predicted ground state. Okay. So what we have discussed so far, we have extracted the phase diagram in the quasi 1D single component dipolar dBEC for that dysprosium atom under the influence of the rotating magnetic field. So where actually we can change that direction of the magnetic field and see the different phenomena. We identified that superfluid, supersolid, and single droplet and multiple droplet, which is forming a lattice. Okay, we observe the shift in the phase domain, okay, of the boundaries for finite field orientations. Okay, by tilting the magnetic field direction, okay. Now what we can see that we can change from superfluid to supersolid, and then we can also form the droplets, single droplet to multiple droplet clusters. We can see that honeycomb kind of structure of the droplets, okay, cluster structure of droplet. So we monitor the spontaneous nucleation of the super solid structures and droplet cluster or area of the quenching in the across the trace. Okay. In the binary cases, what we have observed that different ground state phases, okay, that we have saw that single droplet, we have saw multiple droplets, super solids, okay, and depict the different phases, okay. But these actually we obtained by changing the inter and interspecies scattering length, also using the lambda value. What we haven't discussed that we also change the trapping frequency, okay, and also control all those phenomena that has been discussed. In the miscible phase domain, what we have saw that both the condensate was exactly identical shape as we have seen that. Okay, we have seen the symmetry, okay, in the structure. Whereas in immiscible cases, we observe two types of miscible phases: axially immiscible phases and radially immiscible phases. This has been observed. We haven't discussed this, okay, but it is mentioned in the paper. If you are interested, please have a look. Because of time constraint, I am not elaborating this. Also, by tuning the interspecies scattering length, we observe the dynamical transition from the miscible multi-droplet state to the immiscible multi-droplet state with a multiple domain form along the axial directions. Thank you for your kind attention. I hope that I could convey our work.
Thanks very much, Dr. Sonjoy. Do we have any questions?
I have one question.
Yes, Ranjit, please.
Thank you for your talk. In one of your slides, you mentioned about machine learning.
Right.
My question is, what kind of improvements you are expecting by using machine learning?
So the kind of improvement what we are doing actually, this is another direction of the work. At present, what we are doing using variational quantum algorithm, variational quantum eigensolver. Okay, what we are doing is that we can solving all the differential equations and getting the ground states. Okay, and there actually we implement the machine learning, and this is the area which we are exploring. Okay. Is it?
Okay, thank you.
Yeah.
I think we are running a little bit short of time.
Sorry, actually, I overshot the time.
No. So I want to thank the speaker, particularly for introducing BEC so well at a very understandable level for the students, and also for a very detailed discussion on quantum droplets. Any further questions? I'm sure he will share his email with you all, and I think you should correspond with him. Thank you very much.
Thank you. Stop sharing.
Yeah. Do we have the next speaker here, Dr. Subhashish Sinha?
Yes, I'm present.
Wonderful. So just by way of introduction, first, Dr. Sinha is from IISER Kolkata. And before that, he got his PhD degree at IMSC Chennai, did a set of postdocs, first at Stuttgart, then Max Planck Institute for Complex Systems, and École Normale Supérieure. Now, some of his research interests include ultra-cold quantum gases, non-equilibrium quantum dynamics, quantum phase transition, random matrix theory, etc. Now, the topic that he has chosen today is pretty interesting. It's entanglement, ergodicity, quantum scarring in Bose-Josephson junctions. For a person like me who is interested in dynamical systems, I'm sure it promises to be very exciting. Thank you very much, and I request you to start your seminar.
So thank you very much for this introduction, and let me see if I so let me just share this. So is it visible?
Yeah, it's visible.
Very important role, and particularly the quantum scarring phenomenon. So main emphasis in this work is the quantum scarring. And so as we know that non-equilibrium dynamics of interacting many-body systems has become very interesting research topic in recent years, particularly because of this experimental development in the ultra-cold atomic system, also in the circuit QIQT, particularly the superconducting qubit arrays, etc. So this non-equilibrium dynamics is very important for understanding the ergodic behavior of the interacting quantum system, closed quantum system particularly. So in case of classical interacting systems, it is believed that the underlying chaos or chaotic dynamics that leads to some mixing in the phase space and finally leads to the thermalization. However, in this quantum counterpart, there is no such, meaning this phase space description is not very straightforward. So that chaos or this concept doesn't really hold in this quantum system or closed quantum system. So this eigenstate thermalization hypothesis has been put forward to explain the thermalization of quantum systems, where random matrix theory plays a very significant role. However, it turns out that there are several quantum systems where the ergodicity, it doesn't follow the ergodic behavior or ergodic dynamics. There are deviations from ergodicity. So one of the system is where the ergodicity is strongly violated is the ETH hypothesis is strongly violated is many-body localized system, which typically occurs in presence of random impurity or the quasi-periodic disorder, quasi-periodic potential, etc. The system gets completely localized and fails to thermalize. Also, there are certain cases, it turns out there can be the presence of these non-ergodic states or multifractal states. These give rise to some type of anomalous thermalization behavior, anomalous diffusion, all these types of properties can be seen. So it's some sort of a deviation from the typical ergodic behavior. And most interestingly, the recent experiments, it has been found out that for certain initial configurations, the non-equilibrium evolution of a quantum system exhibits some type of athermal behavior and periodic revival. So this is attributed to the quantum scarring phenomena, which actually shows a deviation from ergodic behavior. So here, meaning in the these types of quantum scarring phenomena has first observed in an array of Rydberg atoms, so which are basically kinetically constrained because of the sort of Rydberg blockage, in fact. So, so in this system, if one start from these dynamics with some density wave-like states, it turns out that it shows a periodic revival phenomena and it fails to thermalize. So it has been also studied very rigorously theoretically, and also turns out that it gives some sort of a fragmentation in the Hilbert space, some sort of type of new symmetry also emerge in this case, and this leads to these types of athermal behavior. And also very interestingly, very recently, these types of spin system can be emulated in the superconducting qubits. And by coupling it appropriate manner, it turns out these types of spin systems can be emulated in the superconducting qubits, and which also shows these types of athermal behavior and scarring phenomena in a controlled manner. One can now do all these types of dynamics. So this is very promising also. But the point is, this quantum scarring phenomena was originally introduced in the context of single particle chaotic system. So where the reminiscence of these periodic unstable orbits, reminiscence of the unstable classical orbits have been identified as a scar of the wave function. So that is the way this has been introduced for the scarred eigenstates by this original work of this Eric Heller. But this connection, in this case, this many-body system, many-body quantum scarring phenomena, this connection with the unstable dynamics is not very apparent or clear, because, I mean, as I already mentioned, the phase space description is not very clear in this case. So to understand or investigate this connection, we considered some collective models like the Bose-Josephson junction and coupled to the bosonic modes. So this Bose-Josephson junction is described in this way, this part. So it is basically, it has been realized in the experiment where the atomic condensate, dilute atomic condensate is loaded in the double well trap so that they'll form a type of two condensates in the left and right well, and there can be a Josephson coupling or tunneling between them. So this part, this J, A dagger, L, A, R, etc., they will just give rise to the tunneling term. This will describe the tunneling between these wells. Also, they are interacting condensates, so they have this type of repulsive interaction. And then we just considered there's a additional some cavity modes which can couple to the left and right wells. And finally, one can write down these things in terms of an effective spin model. So just writing in the Swinger boson representations, one can just get rid of these bosonic variables of the condensate and write it in the spin notation. So this Hamiltonian looks like this. It is reduced to something like a generalized decay model kind of thing. So first term is like minus J Sx, and then there is a repulsion, meaning repulsion times Sz square. And then there is this spin Sz coupled to this effective bosonic mode, which is represented by this B, and this is the frequency of the bosonic mode. Now, this thing is basically under Swinger boson representation. When you just write it in the spin Hamiltonian, this represents a very large spin or the large magnitude. So we can easily go to the classical limit where S is much larger than 1. So spin can be represented by these two vectors, basically, two angles, basically. So it's a phi is a usual angle in the XY plane, and theta is the angle with the Z axis. So we can also introduce another dynamical variable, which are the canonical conjugate to each other. One is the phi and another is Z, which is like a cos theta. So in terms of this dynamical variable, these classical or semi-classical equations can be written in this form. So first part of the Z and phi that represents this Josephson dynamics. And there is a P and Q term that actually represent this harmonic part or the bosonic, the dynamics of the bosonic mode. So this work is done in with my student Sudeep Sinha, and this is the reference. So next, we analyze the different dynamical states of the Josephson junction. In fact, this has been understood without the this external mode. These different branches of Josephson oscillation has been analyzed theoretically and also experimentally they found out. One of the interesting mode I'll focus in this work is pi mode. So I'm not considering the other Josephson oscillation or other dynamical states. So just a oscillation, which is a pi mode, I call it. So it is basically a type of steady states, corresponds to a steady state where the number imbalance is order of 0, but the relative phase between the condensate in the two wells are order something like pi. So this is called because of this phase difference, it is called the pi mode. And of course, in the original, in the experiment, this pi mode has been observed in the Bose-Josephson oscillations. But in case of this bosonic mode, additional bosonic mode, when it's coupled to the condensate, then it gives a very additional interesting features. So it turns out that this pi oscillation, the frequency, of course, it's modified. And moreover, there is a regime where it can become unstable. So the stability regime of this pi mode can be tuned by the frequency of the external bosonic mode, that is omega 0. So we find it has a very sensitive, it has some impact, important impact on the overall ergodic behavior of this system. Moreover, there is another thing that I'm basically not want to discuss in this discussion, in this talk, that is the system also undergoes some type of quantum phase transition, unlike the usual Josephson junction, but it can undergo quantum transition. And we are considering the regime which is after the quantum transition, where the system also shows some enhanced ergodic behavior and also the chaotic in terms of the level spacing distribution. So in this regime, we try to investigate that what is the influence of the stability of this pi oscillation. Typically, this pi oscillation forms at the center of this energy, but not exactly center, but at some energy of this energy band, which is order of classical energy is order of 1. And there we just try to investigate what is the influence of this pi oscillation on the ergodic behavior. From classical simulation, we have seen that when this pi mode is unstable, then it turns out that this phase space becomes completely chaotic, is just mixed up here, like this figure. And when it is stable regime, then we find that there is some sort of stable island appears near this pi mode, and it's a mixed phase space structure that emerges. And its reflection can also form from the quantum analysis also. So if we calculate the entanglement entropy of the eigenstates around this energy density at E1, then we find a very interesting behavior. So when it is just this pi mode is unstable, we find that entanglement entropy of these eigenstates with the increasing energy density that increases and approaches to the maximum entanglement entropy, which is correspond to the page value. But when this thing is stable, for tuning this frequency of this bosonic mode, we find we can make it also stable, this pi mode. Then we find that E is equal to 1, this energy density, there's certain regular structure emerges, and there's a dip also in the entanglement entropy that observed. And moreover, if we calculate this level spacing ratio, this R average that describes the level spacing ratio, and in fact, it contains the very important information about the level spacing distribution. And we know that from the level spacing distribution, the underlying quantum and degree of quantum chaos can be understood, it can quantify. So for when the system is regular, then the distribution, level spacing distribution become Poissonian, and R average goes to takes the value around, say, 0.38. And whereas when this become completely ergodic, then it follows the GOE distribution of the random matrix class, and it reaches the value of 0.53, etc. So there we see the really a nice crossover in the level spacing as this R average level ratio for consecutive level spacing. And also if we calculate the dip, this dip in the entanglement entropy, we find that in the stable regime, stable pi mode, this dip is large. But whereas if we process over to the unstable regime of the pi mode, this dip actually vanishes. So there is a very strong reflection on the stability of this certain dynamical state. Underlying classical dynamics indeed influence the ergodic behavior of the quantum system here. Moreover, when this pi mode becomes unstable, there also we see the sort of reminiscence of this pi mode in form of quantum scars. So we identify in this regime when the pi mode become unstable, we still see that in the Shannon entropy of the states around this classical energy density E1, that there are certain states which have a very low Shannon entropy and deviated from this band of Shannon entropy. So just looking at the careful analysis of this eigenstate, we found out from the Fusemi distribution, which is the semi-classical phase space distribution, we find indeed there is some sort of accumulation of phase space density around this sort of classical fixed points. And also we can see some sort of stable orbits, or sorry, unstable orbits, or accumulation of the phase space density around this pi mode in certain eigenstates. So these eigenstates, one can also construct the semi-classical description of these pi modes from these coherent states, spin coherent states, and the photonic coherent states, the bosonic coherent state. And we find out that these types of eigenstates have the large overlap with this semi-classical pipe description. And moreover, this overlap also diminishes or decreases as the degree of scarring decreases as we enter into the regime where the instability of this pi mode also increases. So this controls the degree of scarring in some sense. So, and another important property I'll mention that about these scarred states is that they violate the Bayes conjecture. In fact, for the ergodic regime, typically these eigenstates, they follow some Porter-Thomas distribution. That basically means that the different entries of the eigenstate, they are behave like a random Gaussian variable. But when there is a sort of accumulation of density in the phase space, then this eigenstates actually deviates from the RMT prediction, random matrix theory prediction. So this way we can see the effect of quantum scarring, how the underlying dynamical state influence the quantum scarring. So next we also investigated two-component Bose-Josephson junction. The similar idea can be tested in the two-component system. So here we consider the same type of double well potential, and where there are two different types of two species of atoms are loaded. So it can be written in terms of this Hamiltonian. So there's alpha, basically the two index basically. Alpha is the site index, left and right, and I is basically the different types of bosonic species. So there are two types of interaction also there. One U is based in the interspecies interaction U, and interspecies repulsion is described by V. So this is also like a collective, can be mapped on a collective spin model. So of two spins basically. We considered the two spins of same magnitude. One is S1 and S2. These are very large magnitude spins. And there's an antiferromagnetic coupling between the spins. And similar way, we can also analyze the classical equations of these spins. So the canonical conjugate variables follow these types of equation. And this work is actually done with my student Devobroto Mondal, Sudip Sinha, and Shayok Ray is a postdoc with Hans Proha. So anyway, so these are the classical equations, and we analyze the different types of underlying steady state structure. By the way, the system is very interesting. So I'm also skipping certain phenomena like the quantum phase transition, dynamical phase transition, and various types of different types of Josephson oscillation or steady states in this model. So just like the previous model, there is also a quantum phase transition, and at the band center, there appears a pi zero mode. So here the pi zero mode is something like this. Then the spin configuration is like that. So one spin is aligned in the x direction and another is in the negative x direction, or vice versa. This way it can represent this pi zero mode. And this mode appears at the band center where the system becomes maximally chaotic. So we study mainly the influence of this pi zero mode on this ergodic behavior of the system. So here we calculate, since we know the classical equation, etc., we can calculate the degree of chaoticity in this classical system from the Lyapunov exponent, average Lyapunov exponent, in the phase diagram of this interaction strength, varying the interaction intra and interspecies interaction U and V. We obtain this type of map of degree of chaoticity. So this blue region shows the less ergodic or less chaotic regime, whereas the red region shows the most ergodic or chaotic regime. And this is a classical picture, whereas we can also try to investigate the degree of ergodicity from the level spacing distribution or the ratio, level spacing ratio, which is called the R average. And as I already mentioned, this R average takes certain values of 0.38 for the regular regime, which corresponds to the Poissonian distribution of level spacing. and R average become 0.53 for the chaotic, which corresponds to the GOE class of random matrix. And we try to see that how the degree of ergodicity varies by this changing this R average or interspecies interaction, and it will be reflected in the R average. So in the color scale, again, we have plotted these things, and we see this resembles same as the structure of the classical degree of ergodicity. So there is indeed some reflection of the underlying classical dynamics on the ergodic behavior of a quantum system, which can be quantified from the sort of level spacing analysis or even from the entanglement entropy, etc. Most importantly, interestingly, we find the regime where the pi0 mode is stable, there the ergodic behavior is less. It's a degree of ergodicity is less, like this blue region where pi mode is stable. That is reflected in both the classical and the quantum system. So we try to analyze also in the other context also. We calculated the sort of Poincare section in the classical dynamics for certain classical energy density, say E-1 and E0, like E-1 correspond to the close to the band edge, which will be less ergodic, so that we see the regular orbits are there. And then there will be E is equal to 0, some mixed phase-based behavior that appears in the classical regime. So now we ask the question whether such thing can be reflected in the quantum analogous quantum system. So what we did, we started from some initial coherent state, which is a semi-classical description of the phase space, and we evolved the coherent state for some time, and from there, from this final state, we calculate the entanglement entropy, and we calculate the its deviation from the maximum entanglement. And that if we plot in this phase space, we find that there is a reflection of the underlying phase portrait there. Okay, that will be the reflection of this classic, meaning whenever there is a regular regime in the local phase space, there is a basically deviation will be large, etc. So next we try to analyze. So previously we have seen that we analyze the degree of ergodicity from the entanglement entropy. But if we look into the entanglement spectrum, that also gives more important information. So what we did, after this in the time evolution of the pi state, we basically looked into the evolution of the pi mode. We started with a coherent state corresponding to the pi mode and dynamically evolved this system, this state. And after the evolution, we see the entanglement property of this state. We find that in the this entanglement spectrum can be separated into two parts. So there are certain parts are having a very large eigenvalue, few of them, few eigenvectors have a large eigenvalue, whereas the others have there is a long tail in the in the entanglement spectrum. And this long tail somewhat resembles with the ergodic states, and the ergodic states have this entanglement spectrum which follows some distribution which is called the Marchenko-Pascu distribution, and this is quite well agreement with that type of distribution. And there is a gap in between these two phases. There is a two gap of this entanglement spectrum, delta lambda. So it turns out that this structure is always there for the underlying classicality. So entanglement spectrum contains two parts. One is the first part is with a largest eigenvalues. They contain the underlying classical behavior. I'll come to this point why I'm calling this underlying classical behavior it retains. And then there's a tail part is like the ergodic part of this. So we find for this pi0 mode can become unstable by tuning the interspecies interaction, repulsion, and when it becomes stable to unstable, then this gap in the entanglement spectrum that also shows a very interesting behavior. It shows a dip, but when this becomes unstable, we find that still this type of gap in the entanglement spectrum retained, and from this gap we can see that how much classical this state is. And this regime, in the unstable regime, when there's a gap, it still has some appreciable value. There, the scarring of this pi0 mode can be found in that cases. So for this gap in the entanglement spectrum is responsible for formation of these scars. Now, why I'm calling these things as a classical? So if we just construct an effective density matrix, effective reduced density matrix from this largest eigenvalues, eigenvectors with the largest eigenvalue, and throw this tail part, then it turns out that the Husserl distribution exactly shows the sort of the density, phase space density is getting accumulated at the classical points, like pi state, pi mode. It is accumulated at this point 0 and pi. So this should happen in this case also. Also, we find, like a previous example, that if we consider the sum of these scar states and the semi-classical state of this pi0 mode, there is a maximum overlap can be found out in these things. Also, the scar state, they have a deviation in the Shannon entanglement entropy, etc. Okay. And also we identified some of these periodic orbits, unstable periodic orbits. And there can be a region where we can find the eigenstate which contains the sort of image of the unstable orbit, also the stable reminiscent, also the stable orbits. So this is a very mixed type of phenomena one can observe in this system. And all these cases we find there is this gap in the entanglement spectrum remains, and this entanglement spectrum separates into two parts. Okay, similarly, this another in this system, there's another antiferromagnetic state appears, and that becomes unstable in certain regime. And we also find out the signature of scarring phenomena of that particular states. So it turns out that these types of steady states or periodic orbit that can be obtained in these collective models can have a reminiscence in the unstable regime, and it will form the scarred states, which give rise to the deviation from the ergodic behavior. So that we also see how it deviates from the ergodic behavior. One quantifying the deviation from the ergodic behavior is the phase diffusion dynamics. We see that it is showing the scarred state shows some sort of revival phenomena in the phase diffusion, but whereas if you consider some ergodic state, then it's on immediately the phase diffusion decays. So it's a phase coherence actually lost in this system. On the other hand, that if you calculate the autocorrelation function and take the Fourier transform, then the unstable periodic orbits, the frequency of the unstable periodic orbits can also be found out from this Fourier transform, the autocorrelation function. In fact, the saturation value of the autocorrelation function also plays a very important role in understanding the or quantifying the degree of ergodicity that we did for this system, where the degree of ergodicity across the band has been analyzed from the phase diffusion dynamics and also from the saturation value of this autocorrelation function. So you know that different energy density as a different types of entanglement entropy is very different, and also this reflected in the saturation value of the autocorrelation functions. Also the phase diffusion. So band age, it is less ergodic, so the phase diffusion is less, whereas in the band center, this phase diffusion is large. So this way one can detect the degree of ergodicity in this system. Energy dependent ergodic behavior, in fact, of this system can be detected. And moreover, these types of scarring behavior, we only considered something, some Hamiltonian system, and we calculated this thing. But in the periodically driven system, these types of scarring behavior can also be analyzed. So we considered a coupled kick-top. It's called actually two spins. And these two spins are interacting via some sort of an time-dependent coupling. It's there. So it's a kick coupled top, like generalization of the kick top is a kick coupled top. And this system also shows a very interesting phase-space behavior, a very interesting bifurcation, etc. So most importantly, there can be a two cycle can be found in this system. Since it's just a discrete time evolving system, so there can be a two cycle, which is a sort of lowest periodic orbit in this case. And we find that this two cycle, when this becomes unstable, their scarring can also be detected in this keep coupled top system. Okay, so various ways, the fidelity, and also there is something called a OTOC these days, the out of time order correlation. All this method can be used to understand or detect the degree of ergodicity, as well as to detect the scarred states or quantum scarring phenomena. So this is also done with Devobroto and Sudip. So finally, I come to the conclusion. So you see that the underlying classicality in quantum dynamics and scarring phenomena can be unfolded from the entanglement spectrum. So that is typically, so the underlying classicality was missing in the, generally it's not very clear how this classicality emerged. So now we see that the underlying classicality can be understood from the entanglement spectrum. And this also gives us another hint that, as I mentioned, that the entanglement spectrum is basically broken into two parts, can be divided into two parts. There is some part contains a large eigenvalue. So this regime contains the sort of classical description, whereas the tail part is like the ergodic part. So if we forget about the throwaway, that just throw the ergodic part, then this classical part, one can construct a reduced density matrix. So this also shows that imply that the a time-dependent matrix product state. If we have just a simple product state, that means just a one eigenvalue, maximum eigenvalue will be there. But if we have 2, 3, or few eigenvalues with the maximum eigenvalues, then one can try to form a time-dependent matrix product state with a lower dimensionality, 2 by 2, 3 by 3, or whatever, the very small dimensionality. And from there, one can try to analyze the underlying classical behavior. So this is an implication of this gap in the entanglement spectrum. And dynamical states like this pi mode in the center of the band center, where the ergodicity is maximum, where this dynamical state play a very important role controlling the ergodic behavior and its regulation. And more importantly, such phenomena can be observed in the collective models like large spin system, which can be realized either in the cold atoms or in the spin qubits, or even in the superconducting qubits. So superconducting qubits now open up the possibility to realize all this system, particularly this keep coupled top. Here we are considering the keep coupled top, but actually just the keep top model has been realized in the superconducting qubit, and the entanglement entropy has been completed. There's a very nice mapping of the classical and the quantum regime. So hopefully all these things, this circuit QIQT setup would be very important role in understanding all this ergodic behavior and its connection with the underlying dynamics. So with this, I will end this talk, and thank you for your attention.
Thank you very much. There is time for questions, if any. Does anybody have a question? Okay, in that case, I just want some clarification. Thank you for the very nice talk. You have seen something like near revivals in a specific case. Have you ever come across a situation where there is entanglement, sudden death? Because that too is a very important phenomenon. So I was just curious.
So no, that entanglement, no, we have not really come across these types of phenomena, but but entanglement meaning there are certain states which shows the deviation from the other states. That's what we found, but not in the dynamical sense we did not find. Like we have found out like there's a deviation, there's a deviated states maybe, but not in the dynamical evolution. There is a certain depth, that type of.
Also, have you, since there is scope for changing parameters, fine-tuning them, have you seen any bifurcations as you?
Yeah. There are lots of bifurcation
Can you
phenomena
please
are happening.
say a little bit? Yeah.
Yeah, actually, this like this quantum. So I did not mention about this all these phenomena. So these systems undergo the quantum phase transition. So classically or semi-classically, if we try to analyze this quantum phase transition, there is nothing but this type of a pitchfork bifurcation. This occurs. So initially, the state looks like that all these spins will be, two spins will be aligned along the x-axis. But after this quantum phase transition, we can see this alignment of the spins in the, there's some Z component also there. And similarly, there can be a dynamical transition, which is not occurring at the ground state. So quantum phase transition is the change in the ground state property, but whereas the dynamical transition occurs at the higher energy states, there also we find a fixed point which where the all the spins will be aligned in the negative direction. But suddenly, after some parameter range, it undergo a dynamical transition like this. The dashed line is there for the dynamical transition. There, it will be spin will become in this particular, will be aligned in a particular direction. Both will be aligned in the same direction, but there will be the Z component will be there. So these types of, and there's another type of steady state will appear. This also is like a pitchfork bifurcation. So typically in these types of system, in the Josephson or the spin models, collective spin models that like a LMG type of spin model, what we are considering here, these have something like a Z2 symmetry, and because of which there is mostly this, we see this pitchfork bifurcation kind of thing. So this dynamical quantum phase transition, etc. Apart from that, there is also a very another type of the transition occurs, which is a bit delicate also, but I just want to mention these things maybe that yeah, there is a, I just mentioned there is a scar of this antiferromagnetic, unstable antiferromagnetic state. So this state also appears as a bifurcation to something it shows. So there are lots of bifurcation, in fact, in these dynamical equations, if we do that.
You are muted.
No, I said thanks a lot for the clarification. I'm just curious if in the classical analogs also you see the bifurcations.
Yeah, these are the classical analogs.
In the quantum, sorry, in the quantum analogs.
Oh, quantum analog also, there will be the, like the quantum phase transition. Quantum analog will be like the quantum phase transition.
So, or the dynamical transition.
Yeah, or the dynamical transition. So that can be observed from looking at the different order parameters. Like here, the SZ average will be something. So after this quantum phase transition, so SZ average meaning there will be the imbalance will be non-vanishing imbalance will be there in that. So that one can calculate. But of course, one has to be very careful in this case that I mentioned there's a Z2 symmetry is there always. So if we want to see the symmetry breaking, then as a slight manipulation would be there needed, like a symmetry breaking field or etc. Or one has to look into the evolution of this gap, energy gap between the consecutive energy levels. If we do the exact diagonalization, and we have to see how this gap evolves in that case. So when there is a transition, it will become very small gap will appear between two symmetry of these parity states, basically.
Thank you. Thank you very much. Are there any further questions?
Yes, I have 3 questions. I don't know whether I have time.
Please ask the first. Let's see.
Thank you. So thank you for your talk. If I understood correctly, you are comparing classical phase portraits with the quantum by using Husimi distribution. So my question is, why do you use Husimi distribution as compared to the Wigner distribution?
Oh, okay. So it's just so first of all, we are not comparing with a like a Husserl distribution, etc. But we just want to find out the classical signature. So underlying classical signature. So after the quantum dynamics of certain states of some semi-classical state, whatever the states we are getting or the scarred state, then we are trying to get we are getting the Husserl distribution. Try to see the whether there is an accumulation of phase space density around the classical fixed points or classical orbits. That was the main motivation. So Wigner distribution can also be done in that case. This is there is no harm. There's nothing special about it. So just I want to see just the classical correspondence of this.
Okay, so from my point of view, Husserl distribution does not show all quantum effects, such as quantum interference. If you take an example, Schrödinger cat state, so Husserl will show you only two spots, but Wigner function, this quasi-distribution function, will show you the interference between these two spots. So maybe in that case, we may lose some information by.
Yeah, sure. It is true that sometimes what is happening that like there's a pi zero mode, for example, in these types of two component boson, etc. There is a two possible way one can construct this semi-classical state. And in fact, there can be a coherent tunneling between these two states that can occur. That is true. So Husserl distribution, we are just trying to look into the the classical phase space where there is a maximum localized points are there. That's the intention. But there, so to distinguish the different thing, whether it's a symmetric or antisymmetric combination or what type of things, is something that is we did not do in that case. Yes.
Okay, thank you. Second question: is there any parameter like Schmidt parameter which can be evaluated to identify whether state is in scar mode or not?
Well, so the procedure is basically something like what the prescription that we followed is something like a search method. So what we did, first of all, we identify where the classical mode become unstable, at which energy density. So we try to look into the eigenstates which corresponds to that particular energy density, and then like this plot that we calculated the Shannon entropy versus GOE, whatever the Shannon entropy, and from looking into the structure of these different eigenstates, we try to see that investigate the different states which have the most deviated in the Shannon entropy. So Shannon entropy is a very less. In that case, these types of states we take and then we calculate the Husserl distribution and try to see whether this contains the reminiscence of the different orbits or not. That's the way we have done these things. And there is another thing also we can do is that if we have the semi-classical prescription of this classical state like this, if it is a fixed point, then it's very easy to construct this classical state from the coherent state, product coherent state, and try to see that whether which states have a maximum overlap with this semi-classical state corresponding to these things, and from there we find the scarred states. So this also is a very delicate issue, as I mentioned, that so the regime where this the states will contain the scar is not a completely unstable regime, which is like the regime where it will become just unstable and still the classicality is retained in terms of the entanglement spectrum, or the the overlap is still significant. In this case, the scar will be appreciable. So one can see that really a accumulation of phase space density. But if we go to the regime where the instability exponent of those classical state become large, the degree of scarring will also lowers in that way. So we actually try to calculate the degree of scarring in our earlier work from these types of deviation of the Shannon entropy, etc., or the overlap function. So it turns out that as we go to the regime where the dynamical instability increases, the degree of scarring in terms of this overlap is also decreases.
Thank you. Last question, what kind of advantages or disadvantages one can have if state is in a scar mode?
Well, so the advantage or disadvantage, I do not know, but point is that it is, of course, it's a definitely interesting. So that is a point, is there's a violation of this in the ergodic regime. If we can identify certain states which has these types of revival or athermal behavior, or more importantly, this non-Markovian type of thing. If something thermalized, then its initial memory will be typically lost. But in this case, it turns out that initial memory is retained in this case. Moreover, it is somewhat nowadays, it turns out that it is related to the fragmentation of the Hilbert space, etc. So if we have a controlled manner, the decoherence, like these qubits systems now there, some sense trying to see there's an application to the quantum information, like in a more controlled manner, one can have a decoherence and all this.
Thank you.
But frankly, I do not know that how this can be applicable to the reality in the real way in the information technology. But as a phenomenon wise, it is interesting. That's.
Thank you.
Are there any more questions? In that case, let us thank the speaker for a very nice talk and for a good question answer session. Thank you very much.
Okay, thank you for your attention. So I'm stopping.